Hello everyone, so welcome to class 3. Today we will look at some tensor algebra, so that so we again, like I said in the last class, all these properties that we have been looking at, the relation between cause and effect are tensors, right. So, there is no way but actually to understand a bit of mathematics about tensors, very simple mathematics, there is no rocket science here. And what is the big deal about these higher rank tensors? What does it actually mean that so a property is a second rank tensor or a third rank tensor and so on and so forth. So, we will try to look at some physical insights into what is all this. Okay. So, the simpler properties, like we discussed in the last class, to understand, or mathematical structure is simple, are the properties that are just simple scalars, or this one property that we said was this pyroelectric tensor, sorry, pyroelectric property, which is a vector, right. So, that is the only vector that I know of, the pyroelectric property pi, right. So, that relates the change in temperature with the polarization that is generated. Okay. So, that is what we did in the last class. So, in the last class we stopped at Einstein notation, right. So, we stopped by saying that if I have a polarization pi, polarization so earlier, if you remember in class 1 in so even a part of yesterday's class, part of the previous class, we were writing P as just susceptibility times electric field, but then we realized that electric field has a direction, polarization itself has a direction, these two are vectors, and chi actually relates to vectors. So, the correct way of writing it is Pi, or the polarization in the ith direction, is susceptibility, which is a second rank tensor, which relates polarization in the ith direction with the electric field in the jth direction. So times Ej, right. So, chi Ij times Ej. Okay. Same thing could be probably said of and this is a very concise notation, it is called Einstein notation. In general, if I have a property small pi, which depends on the cause, sorry, if I have an effect which is given a small pi, it is a vector, which depends on the cause, which is small qi, that is also a vector, or qj, that is also a vector. The tensor that relates these two is the T tensor, T for tensor, right. So, T I j q j, right. So, this is a simple way of generalizing my the Einstein notation. Okay. Now, so what does this notation really mean? That means that if I look at P1, I am going to write P1 as T11 Q1 plus T12 Q2 plus T13 Q3, right. So, P1 is not just dependent on Q1, but it is also dependent on Q2 and Q3, right. So, we will come back to this, and then see what does this really mean. P2, a generalized effect vector, is related by my property tensor T21 Q1 plus T22 Q2 plus T23 Q3, right. P3, again a generalized effect that I am measuring, that is also a vector, is T31 Q1 plus T32 Q2 plus T33 Q3. Okay. So, in general so if we have done some matrices, so I can write P1 P2 P3 as a vector, right. So, is related to Q1 Q2 Q3 through this tensor, which looks like a matrix, but there are a lot of differences. We should not be calling these property tensors as matrices, only in second rank tensor it resembles a matrix, right, a 3 by 3 matrix, but in general these are different, right. So, these are tensors, these are property tensors, they transform differently, then we have matrices that transform differently. Okay. So, I am going to actually come to that by the end of this lecture. Okay. So, this so, and I call this tensor as a Tij tensor. Okay. So, where I denotes so an element in this array is denoted as Tij, right. So, this is one of the elements is denoted as Tij. Okay. So, this is a second rank tensor, right. So, now let us look at our other favorite second rank tensor, which is conductivity, right. So, one is the susceptibility, and the other one is conductivity. Susceptibility is about energy storage, conductivity is about energy loss, right. So we will keep on going parallelly between these two, and at some point we will say that, oh, by the way, these two are related, okay. So but until then, so when I talk about this, I will also talk about this. Conductivity, again to recap your memory, is when I have a force which is electric field which flows some carriers, right. So there is a carrier flow that is happening, physical flow of carriers. Whereas susceptibility or dielectric constant, I have a force that is just displacing carriers, and it's like a stretching a spring and then storing your energy in that spring, right. So in this case, you are stretching the dipole moment, you are creating a dipole moment and storing your electrostatic energy in the dipole moment, right. Both inputs are electric field, the outputs are different, right. So one is a dissipative property, so you have a dissipative output which is flux, and the other one is an energy storing or a conservative property, so you are storing energy, right. So in the form of displacement charges. Anyway, so we don't we don't play favorites. We look at both these properties. These are the most important electrical properties that we look at in this course. So let's come to the conductivity, right. So what relates conductivity? We have simple Ohm's law. What is conductivity, right? So conductivity comes from Ohm's law in a linear regime. So I have an electric field, and I have a current that is flowing. And current can flow, so current density rather. So current density is directional in nature, so it can flow in different directions, right. So if my current density is in the I direction and the applied electric field is in the J direction, then the conductivity tensor, right. So this is a second rank tensor sigma, relates these two quantities, current density which is flowing in the I direction and the electric field which is applied in the J direction, okay. Sorry. Now what does it really mean? So it means that I have a material in which I am applying electric field in this direction, let us say E1 direction, and I am actually measuring current in some other direction, right. So this is J, so the J is, so because of an applied electric field, or if I take a long bar of material and I am applying a voltage in this direction, I typically expect a current flow in this direction, right. So J should be in this direction, right. So the current flow should be in the same direction as electric field. That is what people have taught us all this while, right. But it turns out that is not necessarily the case, because sigma is actually a tensorial quantity, it is a second rank tensor. So I can have sigma in such a way, the components of sigma in such a way that if I apply electric field in this direction, right, so in this horizontal direction, I can have a response which is current in this direction, right. So it is not impossible, right. Now, okay, so people typically talk about so various electronic devices, and there is indeed, okay, so I'll come to that, but in general this property of the direction of cause and effect not being the same comes because the cause and effect are related by a second rank tensor which is sigma in this case, right. So let us assume that sigma, so I can write it in the form of what resembles a matrix, is sigma 1 1, sigma 2 2, sigma 3 3, right. And then I do not have any off diagonal elements in this matrix, right. If that is the case, right. So then if I actually look at what J1 is what sigma 1 1 times E1 plus sigma 2 1 times E2 plus sigma 2 3 times E3, right. So these quantities are zeros, so J1 actually follows E1, right. Similarly J2 will be sigma 2 2 times E2 and J3 will be sigma 3 3 times E3, right. So here the currents are actually following the fields, whatever is the electric field, the current actually follows the electric field, okay. So so for making it much more simple, I will actually make all these quantities the same. Sorry, I have to select the pen, and this is sigma 1 1 and this is also sigma 1 1, okay. So in general so in this very simple case the current follows the electric field. So if I have current in the if I have electric field in this direction, right, so current also follows the electric field, okay. Now all this while, right. So, so in the other courses, right, it is this simple case that you may most probably have been dealing with, right. But this is just a very simple case where my material has, it is a very what is called an isotropic material, where sigma is the same in all directions, right. I do not have any cross components of sigma, I do not have any of these cross diagonal elements of these of sigma, right. So, this is what happens in what are called isotropic materials. We will actually define what isotropic materials are later, but I am just introducing the term here. So, I have what is called an isotropic material, and in isotropic material, so all this while whatever we have been learning, that electric field or current follows the electric field is actually valid, right. But if I make my material more complex, right, so I start putting in sigma 1 1, sigma 2 2, sigma 3 3, but I also start putting in this cross coupling these cross elements, right. So, sigma 1 3, sigma 1 3, sigma 2 3, sigma 2 3. Now, there is a reason why I equate these two, right. So, the sigma or sigma ij is the same as sigma ji, right. So, I will prove this later, but this is a general property of all these property tensors, of lot of these property tensors, right. So, this to be proved later, but for now just assume that this is the case, right. So, whether I apply electric field in direction 2 and measure current in direction 1, or whether I apply so sigma 1 2 equal to sigma 2 1. What does that mean? I am applying electric field in direction 2, that is the cause, and I am measuring the effect is current in direction 1, right. Or alternately, I am applying electric field in direction 1 and I am measuring current in direction 2. These two are the same, right. So, the values of these effects are the same, and this is something that we will prove later on in this course. Okay. So, it is not an obvious statement to make, but the values are the same. Okay. So, that makes sigma what is called a symmetric tensor. Okay. So, in general, this symmetric tensor can be complex in the sense that it can have all these off diagonal elements, right. Now, let us say so my symmetric tensor has sigma 1 1, sigma 1 1, 0, sigma 1 2, sigma 1 2, right. So I mean I am just making up a tensor here. So, the rest of the values are all zeros. Okay. So, this is my sigma of a hypothetical material, sigma hm. Okay. I will call this material, so after my name, I will call this Pavananium, right. So, sigma Pavananium. Okay. So, is this okay. Now, in this material Pavananium, if I actually look at so how J, okay. So, what is J1, right. So, if I take so a block of this, and this is direction 1, this is direction 2, these all tend to be crystallographic directions, but we will come to that later, and this is direction 3, right. So, what is J1? J1 is sigma 1 1 times E1, right. So, and then I apply an electric field. This is the electric field that I am applying, which has components along E1, that is it, right. So, I am just applying an electric field, so a voltage like this. So, just along one component there is electric field, along the other components there is no electric field. So, it is a simple experiment that I am doing. Okay. So, J1 is sigma 1 1 E1 plus sigma 2 sigma 1 2 E2 plus sigma 1 3 E3. There is no E2 and E3. So, these terms do not come. Okay. So, I will just erase it. So, that is fine. So, the current flowing in the one direction is is just sigma 1 1 E1, but if I look at J2, J2 is actually sigma 1 2 times E2, sigma 2 1 times E1. Sigma 2 1 times E1. Okay. So, I not only have a current that flows in my material, and sigma 2 1 is nothing but sigma 1 2, right. So, sigma 1 2 times sigma. I not only have a current that is flowing in this direction, but I also have a current that is flowing in this direction. Okay. And if I do not complete the circuit, so current can't flow, so these charges will accumulate and then they cause a voltage, right. Now, Okay, so that is good, right. So, in this material called pavonanium, by design, right, so of this material, so this material has a property of sigma 1 2 which is non-zero, right. If it has a property of sigma 1 2, I can always have transverse currents, I can apply electric field longitudinally and I can have currents in the transverse direction. Now, if I do not short circuit this, if I do not let the current flow, right. So, in this direction, then so that there will be some transient current that is flowing and then there will be some charge accumulation that will create a voltage instead of generating current. So, I can argue either way. Okay. So, what does it mean that J1 is sigma 1 1 E1 and J2 is sigma 2 1 E1, right. So, if I write the total J current, which is a vector, that is sigma 1 1 E1 in the one direction, I am going to write it as I cap, plus sigma 1 2 or sigma 2 1, they are going to be one and the same, E1 in the j direction, right. So, that means if I have an electric field which is in this direction, then my current, which is I am going to draw it with a blue arrow, is in a different direction, right. This is J, this is E. So, in general, for crystals, so as we will see in later part of this course, for crystals of lower symmetry, right. So, which do not have, are not isotropic or which have lower than there are not so many symmetry elements in these crystals, you can always have these transverse components such as sigma 1 2, right. Now, there is one experiment where okay. So, let us look at this is J equal to sigma E, J I equal to sigma, or capital, I will write it as capital J, sigma I j E j, right. So, this is traditionally the Ohm's law. However, you can also so if I want to measure resistance, what did I say? I am going to apply a current is going to be my cause. So, J j, right. So, small j is the direction, small j is the index, capital J is the current density, times rho I j, where rho I j, where rho is the resistivity tensor, and in this case sigma is the conductivity tensor. So, rho I j j I j should be equal to E I, right. In other words, so the voltage that is generated is resistance times the current, right. So, now what does it mean that a rho 1 2 or cross components exist? Components case, right, are not 0. So, it is the same thing, right. So, sigma is a 2 second rank tensor, rho is also a second rank tensor, and rho and sigma, right. So, these are second rank tensors, right. So, they have a tensorial relation and rho is nothing but sigma inverse, right. So, this is an inverse tensor, right, inverse second rank tensor, it is not just 1 by sigma. I mean in simple case where so if I have an isotropic tensor rho, where sorry, this is 0, this is 0, this is 0, this is 0, that is equal to 1 by sigma 1 1, 1 by sigma 1 1, 1 by sigma 1 1, right. So, in general case, when we talk about isotropic materials such as silicon, germanium, we do not really distinguish what is rho in the as a function of direction or sigma as a function of direction. We just give it one value, we say here is a silicon wafer with so and so resistivity, right. But so if we get to more sort of anisotropic crystals, right, so then we have to worry about what is the rho 1 1, what are the different values of these tensors, right. So, you can ideally have 6 different components for this tensor. Okay. So, now there is, however, one experiment that some of you may know, which is called the Hall effect or Hall experiment, which so you would have seen this cross components being discussed in class, right. So, something like rho 1 2 comes up, or this is equivalent to what is called Hall resistivity. Okay. So, what is Hall effect? Essentially how do you do the experiment? So, let us assume that I have an isotropic material, this is an isotropic material. Later on I will relax this assumption, but for now I am going to say this is an isotropic material, which means to start with there should be no rho 1 2, right. So, the row matrix of the row tensor of this is just row 1 1 row 1 1 row 1 1, only diagonal elements, there are no cross diagonal elements. So, that is an isotropic material. Okay. To start with, I am going to assume that this is an isotropic material. Into this material I am going to send in some current in this direction. So, current is going, or J is going in direction number 1, and I am going to apply a magnetic field in direction number 3, right. So, this is 1, that is 2, and 1 to 2 gives me 3. So, these are my axes, right. So, this is 1, this is 2, and then 3 comes out of plane, right. So, this is a right handed coordinate system. Okay. So, now if I am sending in some current, let us assume current is being carried by some sort of positive charge carriers, holes, right. So, if you did a bit of semiconductor physics, you know what holes are, what electrons are. Holes are these positively charged carriers, right. So, okay, so what happens to these holes when they so I have a positively charged carrier which is moving in this direction, it has a velocity v. The velocity is what is giving rise to the current, right. So, the J1 is related to the velocity. So, these two are sort of related. Okay. So, and on that I am applying a magnetic field, right. So, if I apply a magnetic field, this positively charged carrier sees a force on it, right. So, what is the force on this positively charged carrier? F equal to q, which is just the charge of the particle, it is positively charged, right, v cross b, right. Now, velocity is in direction 1, b is in direction 2. So, so you are doing 1 cross 3, so you should get a minus 2 essentially, right. So, so the force is pointing in this direction, this is the direction of force. Let me write it with a different color. Sorry, I have to select the pen. This is the okay. This is the direction of force. Okay. So, now if positively charged particle has a force which is in this direction, it will try to create some sort of a charge imbalance, right. So, there are going to be on this, once I apply a magnetic field, there is going to be more positive charge that gets accumulated on this face, and less positive charge which is equivalent to absence of positive charge, right. So, there is going to be some charge gradient, right. So, there is more positive charge here and less positive charge, or so in some sense that is more this is more negative than this plate is has more negative charge than this plate, right. So, and as a result, because of collecting because of this charge separation, I am able to separate the charge, I am generating an electric field, right. E, but the E is in direction number 2. Okay. So, you can actually estimate what the value of E is, right. So, I will leave that as an assignment, as a reading assignment. For you to derive this. Where if I have I want you to derive that J that I am applying is equal to, right, V equal to IR. Okay. So, or rather the E2 that I am generating, E2 is the electric field, the transverse electric field that I am generating is related to J, but it is related to J through the magnetic field V3 of course, and some other quantity which is dependent on the carrier concentration. P naught is the carrier concentration. So, to start with, I assume that there are positively charged carriers. So, P naught is the number of holes in this material, right. So, carrier concentration. Ideally, you do not need to assume what is the carrier concentration. So if this quantity turns out to be negative, then you know that the carrier concentration, so carriers are negatively charged particles such as electrons, and your dopant is an n type dopant. Whereas if this term is positive, then you know that carriers are positively charged particles which are akin to holes, or you're p doping the material, right. So P naught gives you the carrier concentration, and so this is something that I want you to prove. Okay. So I will just briefly give you a hint. I said that there is a force on the charged particle that is given as q v cross b, right. Now this force needs to be compensated by corresponding electric field that is being generated, right. So v cross b is in this direction, this is the force, this is the Lorentz force Fl, but this Lorentz force for any sort of static equilibrium to exist should be compensated by an equal and opposite force, right, at equilibrium, which is given as QE2, right. So Q V cross B should be equal to QE2, and so based on that you can get a relation between E2 and J, V has J in it, B3, and other constants. Okay. So this is something that you can derive yourself, or you can so I urge you to derive it. If you are getting stuck, you can look at a standard solid state device textbook. Okay. All right. So let us start from this point, right. Now here I have an EI, so this looks like an EJ, okay, equal to some JI times some rho ij, right. So I have, so this is equivalent of Ohm's law. I have some sort of a cross, or a transverse resistivity. Okay. But this transverse resistivity is not coming because the material is anisotropic. This is coming because I have applied a magnetic field which arises because of an applied magnetic field. P3. Okay. So sorry. Okay. So in general, what people call is, they call this 1 by QP naught term as the Hall resistance, right. So this is RH, or Hall resistance, times B3 times J1, right. So this is actually what is called Hall resistance. Okay. It will as you can see, it will not have the units of resistance, it will have the unit of resistance divided by magnetic field, resistivity rather, divided by magnetic field is the unit of this. Right. So but I mean, from our general framework, the RH times B3 is nothing but it is the transverse resistivity that I am inducing because I have a magnetic field. Okay. Now if I plot, so if I do an experiment where I am actually measuring the E2, or so J1 is a constant, so I am measuring, I am actually going to plot E2 by J1 as a function of magnetic field, right. So which means in my experiment what I have to do is I have to ramp up the magnetic field and ramp it down. So I have to keep on scanning the magnetic field. I cannot do this experiment at a single magnetic field, right. So I have to use magnetic field of 10 Gauss, 20 Gauss, 30 Gauss, 40 Gauss, and then at every magnetic field I have to measure the E2 by J1, right. If I do that sort of an experiment, so from the analysis that we just did, a very simple curve will look something like this, where the slope of this is nothing but your Hall resistance, right, so RH. Okay. However, so if I start with a material which is non-isotropic, in a non-isotropic material, so there is already some rho 12 to start with, rho 12 at 0 magnetic field, right. So, rho 1 2 I mean, so from Hall resistance what we found out was rho 1 2 is a function of magnetic field, it goes as B 3 times R H, right. So, if I already have some rho 1 2 which is at 0 magnetic field, at 0 Gauss, I am just going to write it as 0 Gauss is not equal to 0, right. That means I to start with I have a non-isotropic material where I have this tensor, or so I will just make it different, but I have rho 1 2s which are actually not 0, right, and for simplicity let me just make the rest of them zeros, that is okay. So, right, so I have these transverse components to start with, right. So, these transverse components do exist to start with, okay. Then if I do a Hall measurement on these sort of materials, right, what will I get? I mean, I exactly do the same measurement where I tune the magnetic field. So, I scan the magnetic field and I measure E 3 E 1 E 2 by this sort of a plot, right. So, E 2 by J 1 as a function of B 3. Okay. So, here since there is already some rho 1 2 to start with, rho 1 2 at 0 is not really 0, or R H that you are going to measure at 0 is not really going to be 0, there is already going to be some starting transverse resistance, and then on the top of that I have my Hall resistance that contributes to the rho 1 2 is equal to Hall resistance times B plus rho 1 2 0, right. So, that sort of a thing. Okay. So, at 0 magnetic field you are not going to measure 0 resistance, okay, the 0 transverse resistance, that is fine, but typically a simple way of doing Hall measurements, at least if you have done some Hall measurements in your physics lab. So, what people do is they apply a single magnetic field, right. So, they do not do a scan of the magnetic field like I am explaining here, right. So, in that case, right, so if I apply a magnetic field of this magnitude, let us say, so this is minus let us say 50 Gauss, right, I am going to measure, right. So, in a non-isotropic material I am going to measure E 2 by J 1 whose value is this, right. So, I am going to call it some Y naught. Okay. Now, Y naught is a positive value, B that I am applying is minus 50 Gauss, that is a negative value. This is some experiment conducted in a physics lab. Right. So, for students in a university, right. So, you may have done some lab courses, right, university, where you are not really scanning the magnetic field, you just apply one value of magnetic field, and what are you getting? So, then how do I estimate the Hall resistance? I am just going to use the formula that Hall resistance is nothing but, since these are all linear in nature, it is just going to be Y naught by B 3, right. But if I look at Y naught by B 3, so I am going to look at the slope of that curve, right. So, Y naught by B 3 is negative. Okay. Now, if I do a correct Hall experiment, I get what I just drew here, right. So, this line. But if I do the very simplified form of Hall experiment where I just apply one magnetic field, I am getting Y naught by B 3 is negative. So, what was supposed to be a p type material is now wrongly diagnosed as n type material. Right. And also your Hall resistances that you measure, Hall resist R H values are also wrong. Okay. This may work out, so if you get lucky, and so you do the full measurement, and so you get E 2 by J 1 which is passing through origin, then you are okay, right. But typically that does not happen because of other artifacts also, not just material anisotropy, but material anisotropy is one thing that does not let E 2 by J 1 pass through the origin, right. So, if there is some material anisotropy, this is the ideal case, right. But if there is some material anisotropy, which means I have rho 1 2 even at 0 magnetic field. Okay. Then E2 by J1 does not pass through origin. In the above curve. So, that actually underscores, I mean, the necessity of actually scanning the magnetic field. You have to ramp up and ramp down the magnetic field, you have to and then measure the E2 by J1 at different values of magnetic field, right. So, you have to get several data points and then look at the slope and then say that that is the Hall resistance, that is the correct way of doing Hall measurements. Okay. Okay, but the point being, you know, so even in a measurement such as Hall effect, you have so the point being, even in a measurement such as Hall effect, one needs to consider the material anisotropy and then, you know, do the correct measurement. Okay. Just to summarize what happened in this class. So, I was actually looking at I started by saying we will do some tensor algebra, but you know, so before going into any sort of tensor algebra, we were actually looking at what these cross component tensors are, right. So, especially in second rank tensors, what is sigma 1 2 really mean, right. So, sigma 1 2 is something that relates a cause to an effect, or you know, any generic tensor ij where I is not equal to j, that is the off diagonal element of that tensor, that relates a cause to the effect. But what does that mean? The cause can be a vector, right. So, like an electric field, the cause can be in a certain direction, but the effect does not need to be exactly in that direction, effect can be in some other direction, right. So, this always happens in what are called anisotropic materials, such phenomena, and you know, we do not study them that often, right. But you know, so a lot of materials show such phenomena. Okay. And then we looked at the Hall effect, right. So, Hall effect, we have actually studied that there is going to be some transverse resistivity in the Hall effect, and you know, so we said this transverse resistivity is actually induced by magnetic field. Even if I have an isotropic material, if I have magnetic field, this cross conductivity is induced by magnetic field, because magnetic field breaks some sort of symmetries that exist in the material. Okay. However, even without magnetic field in anisotropic materials, you can have this transverse conductivity. Okay. So, with that I will stop here, and I will meet you in the next class. Thank you.